All right, team, we're working on our exponential growth and decay, and then we're going to also graph exponential functions. So you are going to want your calculator handy today. All right, so every exponential function needs an asymptote. Graphed with it. So we kind of call them partners in crime. Every time you graph an exponential, you have to have an asymptote. They go hand in hand. If you're missing the asymptote, you won't receive full credit. Okay, so every exponential has an asymptote. So let's start with our first graph. It says graph 2 to the x. So let's just talk about what we should be thinking at the moment. This is attached to the x. So let's rewrite our formula. Y equals a times b to the x. And again, it's exponential because the exponent is the variable. Okay, so the number the x is attached to, the b value, is our growth or decay. And again, this should be review. If b is greater than 1, we said it's growth. If b is between 0 and 1, it's decay. Remember, this b value won't be negative. It's either a number bigger than 1 or between 0 and 1. And the number in front of the term attached to the x, a, is called our initial. And that word initial means how many you start with, basically when time begins. So this 2 is attached to my x, which tells me this is the b value, the growth or decay. It's clearly bigger than 1, so I'm expecting to see exponential growth when we graph this. Okay, so we should have a general idea of what we're looking at. So we'll grab that calculator and we'll type in, we have the y equals 2 raised to the x power. And then let's just hit zoom 6, like we always do. And this is what we need to be getting onto our paper. Now again, if they give me a grid, I have to plot exact points. We're not just going to make a quick sketch. Okay, so we're going to go to our table of values. And we're going to start copying down some points. Now, take a look. It happened in the negative x values and the positive. So even though they may not be pretty whole numbers, we still need to graph them all. So let's start with the easy ones. We have 0, 1. And then it looks like 1, 2, 2, 4. What else is going to fit here? 3, 8. Okay, so I took care of the positive x values. Now let's get some negatives. At negative 1, I'm 0.5, which is half of the height. And then I'm a quarter. Then I'm an eighth. And a 16th. I keep getting smaller and smaller. Now, when I look at this graph, to me it kind of looks visually on this screen like it might hit the x-axis. Now let's think about this. If it hits the x-axis, that means the y value, the height, would be 0. Let's look at our table. So as I go back in these negatives, I went from 0.5 to 0.2 to 0.1, 0.06, 0.03, 0.01, 0.007. I don't hit 0. Now wait a minute, what the heck is that? At negative 10, I'm going to arrow over. Okay, it's only going to show a few decimal places, but if you arrow over, it will show you exactly what that number reads. Now, a good reminder from your science classes, this E is scientific notation, and it is telling you to move the decimal, and this negative means to the left, 4 places to the left. So this number is not negative, just to be clear. It would be 1, 2, 3, 4, 0.0009765, which again is pretty darn close to 0, but it's not 0. If I keep scrolling up, I just get more and more scientific notation. Now it's telling me, and I'll arrow over here, at negative 19, I have to move that decimal 6 places, so I'm at 0.000019. I am getting pretty darn close to 0, but you'll notice it is never hitting 0. It just keeps getting these numbers smaller in scientific notation. And what that creates is this fancy word that we have up here called an asymptote. So we want to make sure that we don't actually touch the x-axis. We're going to get close to it. Oops. And we know it goes up forever. I'll put an arrow on the end because it's going forever in both directions. Let's label this y equals 2 to the x. And just like we discovered, it doesn't get to hit 0, it just keeps getting closer. And that's what asymptote means, guys. It means you're getting closer and closer and closer, but you never actually get there. Okay, so how do we draw that? We actually draw a dashed line at what we're getting closer to. And in this case, it happens to be horizontal. So draw that dashed line in. This is what I'm trying to say is partners in crime. Every time you graph an exponential, there has to be an asymptote. Now that asymptote won't always be here, and we'll find examples later. It might be shifted someplace, but it has to have an asymptote someplace. And this is a horizontal line, so it is y equals 0. Okay, so down here it says the asymptote, in this case, it's y equals 0. We've graphed it with a dashed line. Okay, now you'll notice, does the calculator graph an asymptote? No. So you can't rely that the calculator is going to show it to you. You have to lock this into your brain. Exponential gets an asymptote every time. All right, so let's talk end behavior. We spent a lot of time talking about end behavior. The moment I see end behavior, I need that fancy notation. As x approaches infinity, what is f of x approaching? And as x approaches negative infinity, what is f of x approaching? Okay, so I'm going to draw it out as, again, a great review. As my x values go out this way, what is f of x again, guys? F of x is another way to say y. I want to know where the y values are going. So if I go out this way and I look for my graph, it looks like those y values are going to shoot up forever. Okay, and I'm guessing you felt that one was pretty easy. Now, the next one is the one that a lot of people make a mistake on, so let's be real careful. As x approaches negative infinity, so as you go out forever, now be careful, what are the y values approaching? What are the y values? This is your y-axis. What are the y values approaching? It is not negative infinity. The y values, we talked about it, right? We looked at the table even. The y values were getting closer and closer to 0, but they weren't actually getting there, but they're getting closer to it. Now, if you were thinking negative infinity, I want you to think about this. If you were going this way, and the y values were going to negative infinity, that graph would have to come down like that. And it's definitely not doing that. It is not heading towards negative infinity. It is, I mean, it looks like the graph is going that way, but that's not the question. The question is, what are the y values doing? The y values are getting closer to 0. All right, let's look at graph 2. Graph y equals 1/2 to the x, all right? So let's get an anticipation. We know it's exponential. The exponent's a variable. The number attached to the x is the b. The b tells me growth or decay. This number is clearly less than 1 but greater than 0, so I'm expecting an exponential decay graph. I'm expecting it to start high, go low. So let's go to our y equals, clear that out, and we can use our fraction tool, 1/2 raised to the x. Again, a zoom 6 will show us what the graph should look like when we get it on paper. Just as we suspected, it's decay, it's going down. And we're going to do the same thing. We're going to graph that out. Now I'm going to go back and plot out some nice points here. So I'm going to start at 0 again. At 0, it's at a height of 1. And nice points. At negative 1, it's at a height of 2. Negative 2, 4. Negative 3, 8. Let's see, at 1, it's at a half. And then a fourth. And then an eighth. And then a 16th. Now again, look. These numbers, now they're not in decimal this time, right? But they're all positive. Would you agree? As I scroll down, these are all positive numbers. Now again, this calculator is going to start to use scientific notation. This does not mean the number's negative. This means take your decimal and move it 5 places to the left. So at 15, I would be at 0.00003, which is still positive. It is all sitting above the x-axis. Okay, so again, it's getting closer, but it's not touching. So I have y equals 1/2 to the x. Now my brain's got to say, the moment I graph an exponential, I have to have an asymptote. So I'm looking at my picture and saying, this is getting close, this is going up forever, but this is getting closer and closer, but never touching the x-axis. So that is where this asymptote is sitting. Again, it's horizontal, so it's y equals, and it crossed the y-axis at 0. So it's y equals 0. I don't know what that extra equals. Okay, so asymptote again happens to be y equals 0. All right, let's talk end behavior. As x approaches infinity, what is f of x approaching? And as x approaches negative infinity, what is f of x approaching? Okay, so as I go out forever on the x-axis, again, I want to say to myself, what are the y values getting closer to? Not where's the arrow headed necessarily. What are the y values getting closer to? So they were above, above, above. They're still above. They're always going to be above. They're just getting closer and closer to a height of 0. And as x approaches negative infinity, The y values, that arrow's going up forever, so it is going up to infinity. Because again, the y values are going up. Okay, next little section. It says, are the following growth or decay? And these can be a little tricky. So I think there's two obvious growth and decay. See if you can take a moment and put the word growth and the word decay next to two super obvious ones. All right, I would say this is very obvious growth. It's starting low and going up. It looks like our growth that we've talked about. And I would say this is an obvious decay. It looks similar to this graph up here, right? Starts high, goes low. So now, one way to think about these other two graphs, do you recognize that these are kind of flipped over from what we've described as exponential growth and decay? Every time we've graphed growth, we said it starts low and it goes high. And when we've graphed decay, we said it starts high and it goes low. Now, if you take a look at this graph, it looks like it's flipped over, like a reflection. I'm going to go ahead and let's graph this reflection in. It looks like it's a reflection over here. And because it's a reflection, we did our transformations back in November, so I know it's been a while. It just means the exponent was negative, which made it flip over. So this still is actually growth. And we'll talk more about it, but I just wanted to give you a quick example. Same thing on this graph. This one is not, in the shape that we normally describe growth or decay, so I think it's a reflection again in the x-axis. Let's go ahead and reflect that, which just means the exponent was negative, and now I can see that it truly is decay. Okay, but really important, we got these two down, and then the other ones will come as we go throughout the unit here. All right, now believe it or not, you are asked on our exam to usually, sometimes a 4-point question, to literally graph an equation and do it correctly. And you'll be surprised at the number of people in the state that can't graph an equation correctly. Now, you all have a graphing calculator, so it's really hard to screw this up, guys. So we're going to carefully type this in. -6 will open up, I'm going to open up my parenthesis, my fraction, type in my 1/3, close that parenthesis to the x. Okay, so again, I just want to stress, if they give you a graph, you can't just say it looks like this. You have to plot points, right? So you're literally going to go to your table and you're going to plot some nice points. So I'm going to start with the points that are nice. At 0, well, actually I'm going to go zoom 6 so I know what I'm looking at. Okay, so this is the graph I actually want to get onto the paper. Okay, I want to get this graph on the paper. I know what it looks like. I got to make it look like this. All right, so at 0, it looks like we're at -6. 1, 2, 3, 4, 5, 6. At 1, we're at -2. At 2, we're at -2/3. Now, if you don't know what -2/3 is, it's smaller than 1. You could actually type that in your calculator if you need to. -2/9 is smaller than -2/3. Right? We know, by looking at the graph, we know that it's going to go up and it's going to get closer and closer and closer to the x-axis. So make sure that you don't touch it. And again, how do you know you're not touching it? Well, look, do any of these numbers hit 0? No, but again, we're going to get to that scientific notation. I'm not hitting 0. Okay? And they're just all negative under the x-axis. Okay, and then I'm going to nicely connect arrows on the end. End of the graph paper to end of the graph paper. We'll label that y equals -6 times 1/3 to the x. Okay, so is this growth or decay? Now, if you weren't sure by looking at the graph, you should be pretty darn sure by looking at this equation. So let's review again what these stand for. The number in front is the initial amount. So when time began at t equals 0, we started at -6. Makes sense. The b value, right? It's y equals a b to the x. The b value, the growth or rate, is attached to the x. That b value is less than 1 but greater than 0. So I know this should be decay. So if you didn't recognize this as a decay shape, it definitely is decay. We can get that from here. And again, it probably is some sort of reflection over the x-axis. All right, some great words to remember here. Domain and range. Domain are your x values. So you want the x min, comma, the x max. Min, max. So you are looking strictly at the x-axis, right? You're saying, how far to the left does this graph go? Well, this graph is going to keep inching its way out, right? It's going forever to the left. So I'm going to say my x min is negative infinity. And my x max, it's going to keep inching forever this way. So that is positive infinity. We can't reach those, so they get parentheses. My range is now y. Y min, comma, y max. Min, max, min, and then max, always in that order. Okay, so now I'm focused on the y-axis. This graph is going down forever, so it's heading towards negative infinity, the y values. Now, this is the important part, which I didn't graph. Shame on me, I lost half credit here. This graph is going up, and up, but then the y values, they don't go up forever, right? The graph goes out forever, but the y values don't go up forever. They're only ever getting closer and closer to 0. Now they're not touching it, so we're not going to give them a bracket. It's going to stay in the parenthesis. And shame on me, I totally missed my asymptote here, what I'm getting closer and closer to. So let me get that asymptote in there. And let's label that y equals 0. Okay, we're going to go ahead and graph number 5. This is a great time to pause it, so whoever is there, please pause it. Give yourself 2 minutes, graph this, and then answer those 3 questions. Obviously, that shouldn't be rang, that should be range. But this is a great time to pause and then compare. All right, so I've got mine graphed. Again, real simple graph. The calculator is going to do all the work. I have no negative numbers. They're just getting closer to 0. So exponential, asymptote, partners in crime, they got to go together. Clearly, it's growth. As I read left to right, it's growing up. Domain, it's forever going to the left, forever going to the right on the x-axis, so negative to positive infinity. And range, the y values never go below, remember range is y values. They never go below 0, and they go up to infinity. Okay, so now we've got this big review from Algebra 1 here of the growth and decay formula. So if it's growth, we're going to have y equals a times 1 plus the rate to the time. You could divide that by the frequency like we've been doing. And y equals a times 1 minus the rate to the time. And again, you can divide that by frequency like we said. So do you have to memorize these? Absolutely. This was a big part of Algebra 1, I think, or at least it used to be. I still think you do a bunch of this in Algebra 1. So the initial amount. And this is like my b value, right? It's still like y equals ab to the x. But we're proving its growth by saying it's 1 plus a number, right? If this number is bigger than 1, it's growth. So we call that 1 plus the rate. If this number is less than 1, it would be 1 minus the rate to the x or t, doesn't obviously matter, divided by the frequency. So it's truly this equation. We're just showing the growth by saying it's 1 plus the amount or the decay by 1 minus the amount. Okay, now to me, this exponential growth and decay is probably one of the most relatable things that we do in Algebra 2. You've kind of dealt with popular exponential growth through different things, through population growth, cell growth. I mean, some of these can be obviously positive or negative. Unfortunately, if you know somebody with cancer, that cell growth happens most of the time at an exponential rate. The virus, the COVID outbreak we had a few years ago, spread at an exponential rate. Nuclear radiation, when there's a nuclear war, that spreads again exponentially. Decay, sometimes these are positive things, again, or negative things. Chemical reactions, maybe you've talked about in your chemistry class. Prescription drugs, as you take a drug to help heal something in your body, that dosage decreases exponentially in your body. Motor vehicle values decrease exponentially when you drive them off the lot brand new. And again, radiation. So this is something that is hopefully relatable in the sense that you've heard of exponential growth before. So it says, given an exponential function, fill in the table, assume t is measured in years. Let's just underline that t is measured in years. Okay, so you should be able to look at this equation and break all of this down. What is the initial value? So again, I'm thinking y equals a b to the x. The number not associated with b to the x. This is my initial value. I'm starting with 1.4 whatevers. Is it growth or decay? Let's bubble in that b value attached to the t. This is clearly greater than 1, so I know this is growth. Why? B is greater than 1. Now, what is the rate of growth? Well, I basically just need to know how much bigger it is than 1. So I'm going to say 1.08 equals 1 plus the rate. Where did I come up with that from? Well, look at our formula. This b value, right, a b to the x, is 1 plus the rate if it's growth. So I'm saying 1 plus the rate equals 0.08, subtract 1. The rate of growth is 0.08. Now, if I wanted that as a percentage, I would move the decimal 2 places, and I could say, or 8%. How often does this happen? So that's my frequency. If I look back here, it's not technically divided by 1, so I'm going to say every 1 year. All right, let's try the second one. What is the initial value? Y equals a b to the x. Initial value is 25. Do I have growth or decay? Look at this term attached to the variable. This number here, is it bigger than 1 or less than 1? Clearly it's less than 1. That b value is between 0 and 1. Okay, now what is the rate it's decaying by? So let's go back to our formula, a b to the x. If it's decay, it's 1 minus the rate. So I'm going to say 0.35 equals 1 minus the rate. Solve for r, so I'm going to subtract 1. 0.35 minus 1 is 0.65 equals negative r. So it's decaying by a rate of 0.65. Okay, so I'm not saying the rate's negative, I'm saying it's decaying by a rate of 0.65. Okay, or I could say 65%. How often does it happen? What's my frequency? That's what that F is, T divided by F. It is happening every 5 years. All right, next one. Initial value is 100. Is it growth or decay? Looking at this part attached to the X. Hopefully that's very obvious that it is decay. Why? Because a b value is between 0 and 1. What is the rate of growth? So 0.67 equals 1 minus r. Oh, that should have been a negative. That's why that's a positive. I'm going to subtract my 1. So I'm going to get negative 0.33 equals negative r. So my rate is 0.33, or I could say 33%. How often does it happen? That frequency is every 10 years. All right, last one here. Initial amount is 4. Now, growth or decay, super obvious again, greater than 1. This is definitely growth. How would I describe the rate this time? I probably wouldn't say a percentage, so to speak. The moment I say 2, what's another word that represents 2? If you were multiplying by 2, we would say that this growth is doubling. If it was a 3, I would have said tripling, quadrupling, etc. And how often? It's divided by 1 technically, so just every 1 year. Okay, now we've got a few word problems. And I think this goes on to the next 2 pages, so might have to flip. The population of Fruit Bud, New York is increasing, so let's highlight that word, at a steady pace of 2.5% per year. Okay, so you'll notice I do a lot of underlining. The wordier these get, the more underlining we need to do. We know it's increasing, so the moment I see that, my brain is saying growth, 2.5% per year. In order to plan for school growth, the town board would like to mathematically model the future population of the town. At the end of 2005, the Fruit Bud had a population of 6,500 residents. Okay, I think this goes on to your next page. I have to grab mine here. Okay, Determine an equation for fruit buds population as a function of the number of years t since the end of 2005. So you've got all the information you need in front of you. We have exponential growth. So we're going to say y equals a times b to the x, right? Now, they want it in terms of t. So instead of x, I'm going to use t. It says, I need to know the initial and the growth rate. So it says at the end of 2005. So since 2005, how many people did we have? What was our population? I think we had 6,500. That's what we highlighted there. So my initial amount is 6,500 people. Now, we said it's increasing, so we're going to use the growth formula. 1 plus the rate. The rate is 2.5%. Now, we're not putting a percent in, we're putting a rate. So let's make a note. 2.5% equals, we have to move that decimal 2 places to the left. So all of you business people probably do this in your finance classes. 0.025. So plus 0.025 to the t. It's increasing per year. So I'm going to put per 1 year. So I have my initial amount. So again, I'm just going to label these. This is my initial. This is my growth, 1 plus the rate. And this is my time over frequency. All right, part B. Sketch a graph of fruit buds population as a function of time for 50 years following 2005. Be sure to label your y-intercept and your graphing window. Mark fruit buds population at the end of 2055. Okay, so we need our calculator. So let's grab our calculator. We're going to type that equation in. 6,500, 1 plus 0.025, raised to the, and we're going to use x, of course, I need my caret, raised to the x. Now, you'll notice they didn't give you a graph, right? So this is not probably a question you'd see in your exam. Usually they have you, they'll give you a graph and you'll have to sketch this out. Apparently we didn't on here. Now, let's hit Zoom 6. Should make sense to you that we don't see a darn thing on Zoom 6, and I want to talk about why. And hopefully you know why. What was the initial population? Our initial population was 6,500 people. And that is when, remember, initial means when you begin. So when t equals 0, y should equal 6,500. This is a 10 by 10 window. Does it make sense I can't see 6,500 when I start? So immediately, I'm not going to see anything till I get to a height of 6,500. Now this function's increasing, so it's only going to go up. So I think 6,500 is even too small to start at. So I'm going to go to my y max. I know I'm not going to see it till 6,500. I might start at like 10,000 up there. Okay, so I'm just going to tweak that. And now I at least see something. So it should make sense. I didn't see anything till I got to 6,500. We know it's growth, so it's going up. So let's see what else we know. It said for the first 50 years. So let's go back to our window. Okay, I don't have negative time. I don't have negative years, so that can be a 0. And I want 50 years, so I'm going to change this to a 50. Okay, now I need to see the graph from 0 to 50, so I need to go up even more. So let's try, I'm going to try 20,000 just because this thing looks like it's really going. That is close. I still don't see it at 50, so I'm going to go up to 30,000. Now remember, exponential is going to grow fast, so you're going to get these really large numbers. All right, so again, I used 0 to 50 because it said the first 50 years, and I ended up at a 30,000 for my y max. So I'm going to make a sketch like it says, and it says label your y-intercept, which is 6,500. That's our initial when time begins. And it says mark your graphing window. So I'm going to say x min was 0, x max was 50, y min was negative 10, y max was 30,000. Mark your fruit buds population at the end of 2055. So this represents 2055. Okay. So if we went 50 years, and this started at 2005, so I want to know what my population is at 2055. So I basically just want to plug in 55 years. So I'm going to say y equals 6,500. Just got to copy my formula down. Okay. So y equals 6,500 times 1 plus 0.025, the t. Now we said that's 50 years later, so I am going to plug in 50 for t. And I'm going to go to that home screen and just type that in. 6,500 times 1 plus 0.025 raised to the 50th power. And the population should be 22,341 people. Part C says, use your model from Part A to predict the number of residents at the end of 2010. Round to the nearest person. All right, so let's start with our formula. 6,500 times 1 plus 0.025 to the t. Now I want 2010. Okay, now think about this. This represented the population at 2005. And t is the number of years. So I am not putting in 2010. That is not what t is. T is the number of years since the end of 2005. So this requires you to read the number of years since the end of 2005. So 2010 is how many years since 2005? 5. So all we're doing is plugging in 5. Okay, so I've got 6,500 times 1 plus 0.025 to the 5th, and it said to the nearest person, so 7,354 people. All right, graphically determine when the population reaches 10,000. Okay, so let's get our graph going again. We're going to resketch that graph quickly. This was 2005. This was 2055. This point was 6,500. We want to know when the population reaches 10,000. So just to be clear, we are looking for the time. We want the time when the y value is 10,000. Okay, we don't know the time. That is the question. Determine the year, determine the time. So I'm going to take my equation, my 6,500 times 1 plus 0.025 to the t. I don't know t, but I want this to equal 10,000. And that setup should make sense to you. I don't know t, but I want it to be a population of 10,000. Now, you can't solve this by hand yet. It is impossible. So that's why it says graphically do this. And we've solved these systems graphically, actually. We said you're always going to put one equation in y1 and the other side in y2. Now, the good news is you should already have this equation typed in y1. All we have to do is go to y2 and type in our 10,000. So we're going to write our equation out. We're setting it equal to 10,000. One piece goes in y1, one piece goes in y2, and we're going to hit graph. And then we are going to graph this on our paper. And anytime we graph two things, we are looking to find where they intersect. And where they intersect will be our answer. So we're going to go second, trace, intersect, enter, 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 and it should say intersection eventually. So second, trace, intersect, and we should get at t equals 17.445. And it says to determine the year, so I'm going to say the actual year would be 2005 plus 17.445. Would be in the year 2022. All right, next example. The population of a town is decreasing by 4% per year and started with 12,500 residents. What is the projected population in 10 years? Okay, highlight, highlight, highlight. Decreasing. The moment you see that, your brain's got to go exponential decay. That's the formula I'm going with. 4%. I got to figure out what the rate is at 4%. That's the percentage. I'm going to need the rate. It started with 12,500. Started with means the initial amount. Okay, so if I have a percentage, we said move the decimal how many places to turn it into a decimal. Okay, so my rate would be 0.04. To go from percentage to a rate, I move 2 to the left. To go from a rate to a percentage, 2 to the right. It's always 2. All right, so I have y equals, the initial amount is 12,500. It is decay, decreasing, so it's 1 minus 0.04, and it decreases 4% per year, so t over 1 years. Initial, 1 plus or minus, I'm going minus because it says decreasing, 4% to the year. Now it says how much will the population be in 10 years? So that's telling me t equals 10, plug in 10 for t. Y equals 12,500 times 1 minus 0.04 to the 10th. Plug and chug on your calculator. I'm going to skip the calculation part for a minute. All right, I want to set up this last problem. The number of students at Frontier High School who have the flu is increasing, ding, 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 exponential growth, at a rate of 12% per day. Underline those units. In the beginning of Monday, there were 66 students beginning, aka the initial, with the flu. Approximately how many students will have the flu on Friday? All right, so let's get our function written. Y equals A times 1 plus or minus the rate to the t. It's increasing, so we're going with plus. The initial amount is 66 students, increasing at 12%. So that's 1 plus 12%. To change that to a decimal, we're going 2 places to the left, 0.12 to the t, each divided by 1 days. This is represented in days. All right, so the question is, how many students will have the flu on Friday? So if this was Monday, that's Tuesday, Wednesday, Thursday, Friday. I'm plugging in how many of them will have it in 4 days. I'm going to let t equals 4. So I'm going 66 times 1.12 to the 4th. And again, plug and chug on your calculator to get that answer. Well, that does it. We've got some great practice tonight. Take your time. Some of them get a little tricky with the units, so be super careful.